Hello, and welcome back. This week we're going to transition into chemistry, and we're going to start with chapter 12 on atoms and the periodic table. So the lecture will help you understand that atoms are ancient and empty. We're going to talk about the elements themselves, protons and neutrons, the periodic table, something you do not need to memorize, periods and groups, the physical and conceptual models of the atom, identifying atoms using the spectroscope, the quantum hypothesis, and electron waves and the shell model to end with. So we do know that atoms are ancient. Their origin of most atoms goes back to the birth of the universe, and most of them have empty space inside. And so elements heavier than hydrogen and much of the helium that we have was produced in the interiors of stars. So what is an element? An element is simply a material made of only one kind of atom. Pure gold is an example, as it is made of only gold atoms. The atom is the fundamental unit of an element, and so the term element is used when referring to macroscopic quantities. The term atom is used when discussing the submicroscopic level. And so atoms make up all the matter around us. To date, there are 115 distinct kinds of atoms, 90 of which are found in nature. The remainder are synthesized in a lab. And so we already mentioned an element is a material consisting of only one type of atom. So what's inside the atom? We have protons and neutrons in the core. And so these protons, think of positive protons, carry a positive charge. It's the same quantity of charge as an electron, which is negative. They're about 1,800 times as massive as an electron, the protons are, and have the same number of protons in the nucleus as electrons surrounding the nucleus of an electrically neutral atom. So what are the electrons then? They are identical. They repel electrons of neighboring atoms and have an electrical repulsion that prevents atomic closeness. So when dealing with protons and neutrons, we have an atomic number. And this is simply the number of protons in each element listed in the periodic table, which we'll show you here in a few minutes. The neutrons accompany the proton in the nucleus and have about the same mass as protons, but no charge. They are neutral neutrons. So both protons and neutrons are called nucleons. And so now what are isotopes and what is atomic mass? An isotope refers to atoms of the same element that contain the same number of protons but different numbers of neutrons in the nucleus. They are identified by a mass number, which is the total number of protons and neutrons in the nucleus, and they differ only in mass and not by electrical charge because isotopes share many characteristics. And so the total number of neutrons in an isotope is the mass number minus the atomic number. So the atomic mass now we will define as the total mass of the atom's protons, neutrons, and electrons, all of its properties. This is listed in the periodic table as an atomic mass unit. Now, we don't have to memorize this, but we'll define an atomic mass unit as about 1.6 times 10 to the negative 24th of a gram. So we're talking extremely microscopic numbers here. Okay, the periodic table is a listing of all known elements, and we're not going to memorize it, thankfully. We're going to learn how to read it. And so a chemist uses a periodic table much like a writer uses a dictionary. Neither of them need to be memorized, and most chemists don't have it all memorized. So here it is. We can see that number 1 and number 2 are the most important and the most abundant in the universe, hydrogen and helium. And so the elements are highly organized within the periodic table. Each vertical column is called a group. Each horizontal row is called a period. And so here we see mainly 7 periods here, and we have about 18 groups in this diagram. And so we have different types of metals in this group. We have halogens, we have noble gases in this group. So they're all lined up in their properties. So we can talk about physical and conceptual models of the atom. A physical model replicates the object at a convenient scale. We do this in astronomy too. We have a celestial sphere, a globe that represents the night sky. It's just a more simplified version. The conceptual model describes a system with words. And so the atom is best described by a conceptual model. Now we can use an instrument called the spectroscope, which separates the elements into their component parts. And so we can have analysis of light emitted by the elements which they are made to glow by a heat lamp. They identify each element by a characteristic pattern of a spectrum. There are lines in a rainbow. So each element emits a distinctive glow, such as neon emits a red glow. Sodium emits a yellow glow. You might see in your neighborhood the street lights, you might see some light blue or white ones. And you might see some yellow ones. The yellow ones are a cheaper, more economic version of sodium gas, whereas the blue ones and the white ones are mercury gas and use up lots of energy. So the atomic spectrum is an element's fingerprint, a pattern of discrete and distinct frequencies of light. The discovery of the atomic spectrum of hydrogen was done in the 1800s. A researcher noted that hydrogen had a more orderly atomic spectrum than others did. Johann Balmer expressed line positions by a mathematical formula, and Johannes Rydberg noted that the sum of the frequencies of 2 lines often equals the frequency of a 3rd line. And we see that in sodium H and K lines. So here we have the red glow of strontium and in its spectrum, potassium, and we have lines here that match up with potassium. Barium and copper have particular lines. And so when we heat up these elements, we excite the electrons. And so the electron can gain some potential energy and moves further away from the nucleus, and a photon of light is absorbed. If that same electron were to go down closer to the nucleus, then it loses potential energy and a photon of light is emitted. There are 3 transitions possible in an atom, and the sum of the energies and frequencies for jumping from A to B is the same to jump from A to C. So now let's talk about the quantum hypothesis. Max Planck, the German physicist, hypothesized that warm bodies emit radiant energy in discrete bundles called quanta. The energy of each energy bundle is proportional to the frequency of the radiation. Einstein further went on to state that light itself is quantized. A beam of light is not a continuous stream of energy, but yet consists of countless small discrete quanta of energy, each quantum called a photon or a light beam. So we ask the question in physics and chemistry, is light a wave or a stream of particles that we call photons? Well, it can be both, actually. Light can be described by both models. It exhibits properties of both a wave or particle depending on the experiment. And the amount of energy of a photon is directly proportional or similar to the frequency of light. So using the quantum hypothesis, the Danish physicist Niels Bohr explained the formation of atomic spectra as this. The potential energy of an electron depends on its distance from the nucleus and the shell that it's in. We'll get to shells here in a minute. And when an atom absorbs a photon of light, it absorbs energy as well. So the low potential energy electron can be boosted to become a high potential energy electron in a higher shell. Using the quantum hypothesis, it further says that when we have an electron in any energy level drop closer to the nucleus, it will emit a photon of light, which we've discussed now. And Bohr reasoned that there are distinct energy levels within the atom. Each energy level has a principal quantum number called n. It is always an integer. The lowest level is 1 and is closest to the nucleus. So Bohr's model also explains why atoms don't collapse. The electrons can lose only specific amounts of energy equivalent to the transitions between those levels, those shells, the n numbers. And an atom reaches the lowest energy level called a ground state when the electron can't move more energy and can't move any closer to the nucleus. And we can look at also the planetary model of an atom, where photons are emitted by atoms as electrons move from a higher energy outer level to a lower energy inner level, and the energy of the emitted photon is equal to the distance and energy between those two levels. And so because the electron is restricted to those discrete shells or levels, only lights at distinct frequencies are emitted. And so we have electron waves, which an electron wave nature explains why electrons in an atom are restricted to those energy levels. Permitted energy levels are a natural consequence of ascending electron waves closing in on themselves in a synchronized manner. So the orbit for an n equals 1 ground state consists of a single wavelength. N equals 2 is of 2 wavelengths, and 3 is 3, and so on. And so for a fixed circumference, only an integral number of standing waves can occur, and likewise in the path of electrons about the nucleus. And so this is like a cutaway of the shells of those energy levels. We can talk about them in terms of shells, where the ground state only allows 2 electrons. The n equals 2 state allows 8 electrons, and we go further and further out. And so here is a shell model on the periodic table. We'll end with this, and that is our first chapter in chemistry, chapter 12, Atoms in the Periodic Table.